And thank you everyone for sticking around at the tail end of XAIP. They saved the best for the last. So hi, I'm Ram. I'll be presenting this work on accounting for how humans make policy execution errors in MDPs. This is joint work with Mudit Verma and Dr. Subbarao Kamambati. So what's the point of computing an optimal policy in an MDP if the agent is going to execute it suboptimally? This was the motivation. When humans execute a policy, there are two main parts. We identify what state we're in and execute the associated action for that policy. Now, there are some problems that could occur because of this. The human may take longer to identify the state if there's confusion or uncertainty. And if they misidentify the state, then the wrong policy action may be executed. Now, for this work, we assume that the human has access to the policy or has it perfectly memorized. And we're limiting the problems to problems that arise from state misidentification, which are these two things: the delay from confusion and executing the incorrect action because you chose the wrong state. So there are different modes in which the human may be executing the policy. There's no errors. This is the perfect human. That's boring. Let's consider the other modes. It could be that the human only results in delays of execution, where because the states are confusing, they take a little longer to identify exactly which state they are in. So they may take longer, but they end up getting the right state every time. Another mode is they only commit the policy error, which is they get to see the state once, and because they have to act quickly, they don't spend time re-identifying or re-verifying the state. So the only type of error that could occur in such a scenario is the execution error from misidentification. And the most general case is that you both have delays in executing the policy because of the human spending time observing the state, and they may still get it wrong and execute the wrong action. So to give you an intuitive idea of what I mean by state aliasing and similar states is a simple stochastic shortest path problem on the right. The goal is to get to the bottom right, and both of these policies are optimal. They get you there, but one policy is clearly simpler. And if the human's confusion has to do with which position they are in, say by L1 distance, then giving the bottom policy, the simpler policy, is going to give you better results. They'll execute faster and there's less likely of any delays. So the idea of similar states can arise due to feature similarity, which comes from visual or perception errors, and there may be shared features. So you just pay attention to the shared features due to stress or speed. There's inattention problems, and you may confuse the states. So let me drive it home with an illustrative example of a warehouse worker, a packer in, say, a company like Amazon, where their task is to look at the package or order and all the elements of it and figure out which box to put it in. The optimal policy is finding the exact right box and determining if bubble wrap is needed or not. Now, this could take a long time. They may get the wrong box, and if they have to remove it and put it in the right box and then correctly decide to add bubble wrap or not, you're dealing with executions and delays. However, if the cost of using a larger box and always using bubble wrap is significantly lower than the reward that the company gets by just shipping out products faster, then using a simpler policy that may seem suboptimal is better and is actually optimal because it's a human who's executing it. There's less delays, less errors, and more products are going out. So how do you get these state confusion probabilities? We're assuming that the human has a perception policy. This could be trained by, for example, in the warehouse worker, they may be trained to look at the biggest product in the order and guess or use that as a heuristic to find the box size that's needed. Or it may be variable depending on the situation. But all we care about is getting the likelihood of confusing state S1 with S2. And we can get these statistics empirically by just evaluating the human in different states and getting this information. So how do we compute the probability of the human taking another identification action and causing this delay? Well, the only time a human would actually bother about verifying their state is if the policy is different in the two confusing states. So if I think it's state SI, but it may also be state SJ and I'm uncertain, it doesn't matter if the policy is the same for both states. I won't need to re-verify that particular state identification. So the likelihood of the human taking this re-identification action depends on the policy. This also changes the deterministic policy that we give to the human into a stochastic policy, since the likelihood of state re-identification is determined by that policy. Now, what about the other type of error, where the human executes the wrong action? The policy post-confusion is determined by the likelihood of confusing a state with another state, which is the phi s s prime, times the probability of taking that action in that state. Now, since the policy we give to the human is a deterministic one, that pi s prime a will either be 0 or 1, but it becomes a stochastic policy due to the state confusion probabilities. Once we determine the stochastic policy that occurs during execution, we could get the value of the associated policy, because the MDP becomes a Markov reward process once you fix the policy using this closed form computation. So having talked about all these pieces, how exactly do we find these nice policies that account for human execution errors? We use a simple hill climbing search approach where you iterate through the states and take that action, which improves the overall state value. And the reason why we have to consider the overall state value and just not local value iteration is because the policy across states are coupled, since the human can confuse two states that are similar. So it's a simple hill climbing approach, and we use this weighted function in order to compute the value. Notice that the value of a state is in the denominator. So we go in the opposite. We don't go for increasing value, but decreasing value. The reason we do this is because we want the state value of all states to be increased at the same time, not just one state. So doing 1 over x and minimizing it actually improves the search outcome. And since this is hill climbing search, we do random restarts to get better results. Now, this search process handles all the execution modes that we talked about, the only delay, only error, both delay and error. However, some of you may have realized that if we only consider policy errors, this actually is the same problem as computing a reactive controller for POMDPs. Now, Littman in '94 showed that this problem is NP hard, but they did find a branch and bound approach for finding the optimal policy in stochastic shortest paths. In their approach, they use a hill climbing subroutine to find the bounds. We have not incorporated this into our approach yet, but we will adapt it similarly. Another methodology one can use if you only consider policy execution errors is computing it with history-based controllers. This is work by Akshat Kumar and Shlomo Zilberstein, where the subroutine in their approach returns a reactive control on the first step. So plan to reach out to them and get the code to compare with our method. Now, thus far, we've been computing the policy to just account for the errors, but we really care about these poor humans. We want to make their policy even easier. How do we do this? We quantify a confusion score defined as such, which is we consider for every pair of states that can be confused with each other, if the policy is different, then it's more confusing. So if in a grid world, if all the positions around the same tile have different directions to move, that's a much more confusing policy than if they all go down. So in that way, we can quantify a confusion score for a policy. Given this confusion score, we can weight the hill climbing search to consider minimizing the confusion score as well as the value, as well as optimize the policy value using this omega hyperparameter. These are some early results in a simple 10 by 10 grid world with stochastic shortest path. All I want you to take away from this slide is that the optimal policy, which is on the extreme left, sorry, let me rewind a bit. On the left is the graph for expected policy value as we vary this parameter for searching for simpler policies. The very first entry is the distribution of policy value for the optimal MDP policy. This is after we consider the execution errors that the human does. Notice that's lower than the policy computed by our method, especially when omega is small. As we increase omega along the x-axis, the expected policy goes down, although there's a lot of variance in between. But the confusion score also goes down, which is seen on the plot on the right. We also did human studies to actually verify if these phenomena actually occur when a human is executing a policy and not just our wishful thinking. We had 40 participants in an MTurker study, and we displayed either a simple policy, which is the policy on the left, or a complex policy, which is the policy on the right. What the human had to do is we would display a color, and they would just have to press the corresponding arrow. Now, it may not be easy to see, and that was the intention, that each of these shades of red, green, and blue are slightly different. So it's going to take a little longer for a human to distinguish between those shades of red and choose the right action. Another point of note for this experiment, we showed both simple and complex policy to the same participant. So we were able to test their performance, same participant, both policies, for 1 minute each. And the results showed that with the simpler policy, you have a lot higher correct attempts, and the total attempts, it's statistically significant. However, the error rate was not statistically significant at the 5% level. The p-value is 6.5%. It could be because humans were just spending longer to observe the state and trying to get it right rather than rushing to execute the action. That would be error mode 1, which is only policy delays. The point being, we were able to see the phenomenon that we expected when humans are executing policies. So to put it all together, when humans execute a policy, there's a delay if it's not easy to distinguish between states, and they might misidentify and execute the wrong action. These two have to be accounted for when you compute policies to give to humans to execute. There are 4 possible modes of error, where no error, only delay, only execution error, and both. We also compute a confusion score and allow our algorithm to trade off between the expected policy value and confusion score to look for simpler policies. We also did human studies to see if this phenomenon actually translates to the real world. Thank you. And I just wanted to say we used this resource for the icons in the presentation. I'll be happy to take any questions, and thank you for listening.